When did you have to leave home? On level 7? 7:15? 7:05?
Which one? One.
They take time.
I guess I was starting. I was starting.
7:05? 7 o'clock. Oh, this is the interest bad.
That's fine.
2022.
4 years.
What
Is
for
it 4 years?
2 years?
Yeah, that's the same as I. So do I.
Yeah. Take a look. You look the same. Aren't you supposed to, like, grow longer hands and grow taller? Morning, Josh.
Didn't realize it was class today.
On Monday, I'm planning to take the class off. It's a rare class on Wednesday. Monday's the eclipse. You're presenting diffusion on?
It should be Wednesday.
Oh, no. Because Wednesday is carnival.
Wednesday's not Carnival, Thursday is.
So, yeah, but Wednesday is also a break due to carnival.
Yeah, I'll tell you what. We'll just push it back, that's fine.
All right, so there'll be no class on Monday.
So no class Monday, and then I'll teach the week we get back from Carnival.
Or you could teach on Friday.
No one's gonna be there,
Yeah, that's right.
I'll teach the Wednesday we get back from,
You just got yourself 5 extra days.
yeah.
You can literally thank the sun and the moon. When did you ever get a chance to do that?
I get to move the heavy to nurse and not teach.
Morning. See, look, here's the story for your life.
Gary.
He gets to thank the sun and the moon for 5 days extra for his lecture. It's an ideal.
Hey, Misha.
Whatever, let's do ideal.
Misha, I want that coat you had from Rwanda.
Which one?
Or was it from Rwanda? The tan one.
Oh yeah, it's too small for me.
Well, I don't want that one.
It's too small for me. It's going to be, you barely get one arm in. All right, folks. All 5 of you. 6? Okay. 7. We have double-digit students, so I think I can start. The attendance score is 1758 for those of you on Zoom. This is my way of checking whether you're actually on, paying attention or not. I don't have my microphone today. Okay. So for the next couple of lectures, we're going to be talking about variational autoencoders. And the lecture after that, we will speak about diffusion models. There's going to be no lecture on Monday because it's the eclipse. And I figured some of you would want to see the eclipse, at least I do. So, in fact, LTI is letting some students travel up to see the eclipse up north. And so, since considering that these opportunities come by once in so many years, I might as well, right? So you get Monday off. Okay. So here's where we were. Neural networks, we saw, are universal approximators. They can model Boolean functions, classifiers, regressions. They can be feature extractors, as we saw in the last class. And they can be classifiers and predictors, right? All of these are doable. But then here's a new problem. In all of those cases, we were looking at doing deterministic things, where I provide an input and it computes an output. Now the neural network is essentially a function of some kind, right? They operate on or process a given input data, and they learn to perform these tasks from data. But can networks generate data? Instead of just operating on data, can they actually generate data, and can they learn to do so from examples? That is the topic for the next series of lectures. So here's the problem. You're given a large collection of images, let's say of faces, and the question is, can the network learn to generate a new portrait just from seeing large examples of pictures? A new portrait of a completely fictitious person. We know it can do it, but then what is it that we're actually doing? We are learning the distribution of faces, and we are drawing a new sample from this distribution. How can we train a network to do that? Or let's say from a large collection of landscapes, can a network learn the distribution of landscapes so that it can learn to generate new landscape pictures which have never been seen before? So once again, this means you have to characterize the distribution of the images of landscapes, and how do we characterize it? So in all of these cases, we are really speaking of neural networks as generative models. I wonder if I can. No, I don't have my clip-on mic right now, unfortunately. So we want the network to actually be able to model the distributions of data so that we can draw samples from it. That's the new task. And this means that we want the network to be able to generate data, right? You want the network to operate as a generative model. So what is a generative model? We'll take a look at that first. What are generative models and how to estimate them? And we'll look at a specific mechanism for estimating generative models, namely expectation maximization. Well, I'm kind of misstating it. We're not going to be looking at EM per se, but a mechanism that is related to EM, of which EM is one instance. So what is a generative model? It's a model to model the probability distribution of data. For example, a multinomial distribution or a Gaussian. These are generative models. Now, computationally, you can think of these as models that can be used to generate data with a distribution that's similar to some given data X. And so you can think of the generative model as some kind of a box. Every time you poke it, it's going to generate a sample from a specific distribution, right? So just at a very high level stuff. So here's the notion behind generative models and how you learn them. You are given some collection of data, for instance, a collection of images. You choose a model for the distribution of these data. So the fact that this is a model is characterized by the fact that we are representing it as P of X semicolon theta. The symbol theta represents parameters of the model, and the fact that this is dependent on parameters means that it's a model and it's a parametric model. And so when I'm trying to learn a distribution for a given data, I'm trying to estimate the theta such that P of X semicolon theta best fits the data that I've seen. Now, all of this is abstract. Let's try to look at this from a more concrete example. Let's say I have a dice. I've rolled it many, many times. It's a 6-sided dice, so there are 6 possible outcomes. And I plot the histogram. So the histogram I get is the colored histogram to the right. And now, obviously, anytime you roll dice, the histogram that you're going to get for the outcomes is going to change from experiment to experiment. So I give you two options for the probability distribution of this die. They are shown to my left in blue and green. Of these two options, which one would you think was more likely to be the probability distribution for the dice? Anyone? Which one would you choose? The second one? Meaning the green one, right? Okay. Why?
It's similar.
It's similar. That's a pretty good. So what is the assumption you made?
The distribution of the outcome of the expected outcome should be similar to the input distribution.
That's right, right? So here's another example. I have a histogram of outcomes of draws from a Gaussian distribution. In fact, these are real data. These are features derived from a speech recording. And suppose I told you that I have plotted three different Gaussians to the right, the red, the yellow, and the green. And if I were to ask you which of these represents the actual probability distribution that I drew these samples from, which one would you choose? The red one again. Why? It looks just like it, right? Now, how do you quantify looks just like? So, the assumption that you, implicit assumption that you made is that the world is a boring place. Right. It's so boring that anything that you see is very typical. There's nothing atypical about anything that you see. So this means that you assume that the data that you got from this example, from this experiment, was very typical of that distribution, which is why you expect the distribution of the data to match to be similar to the Gaussian. You expect the distribution, the histogram of the outcomes of the dice to be similar to the distribution. So I can flip this argument around, right? If I want to estimate the probability distribution for a random variable, I'm going to start with the assumption that the observations I got are very typical because the world is boring. So given a choice of many different distributions, the one I chose was the distribution for which the observations I got were most typical. Isn't that what we did? Right? So I can take that argument to the extreme and say that if I want to estimate the probability distribution for a given set of data, I'm going to select the distribution that has the highest probability of generating the data. So the distribution I choose must assign lower probability to rarer observations and higher probability to higher observations. So of all the probability distributions in the universe, you're picking the one for which the data you observed are most typical. In other words, you're picking the one which has the highest probability of having generated the specific data that you have observed. So this is the world is a boring place hypothesis. That's what has got a different mathematical name. It's called the maximum likelihood principle. And so here's how the maximum likelihood principle works. Let's say you're given a collection of data like the histogram to the top, or the Gaussian distribution, the histogram at the bottom. In the one to the top, that's a histogram of draws from a dice, and the one in the bottom is a histogram of draws from a Gaussian distribution. And in each case, we want to pick the specific model for which the probability of this observation is largest. In other words, you want to pick the theta such that P of x semicolon theta, where x represents the data that you have, is maximized. And we can work through the math, right? Very simple. For the histogram, the probability distribution of the outcomes that we just saw is simply going to be the product over all possible outcomes of the probability of the outcome raised to the number of times it was seen, assuming every single draw was independent. For the Gaussian, the probability distribution of the outcome is going to be simply the product of the probabilities assigned to each of the outcomes by the Gaussian. And this is what you're going to maximize, the probability, the cumulative probability of all the training data that you've got. And since the logarithm is a monotonic function, instead of maximizing the probability, you can maximize the log probability. And the reason we take the log is that the product of probabilities becomes the sum of log probabilities. So, which means that you can treat each independent observation independently. And this is what you would maximize when you're trying to estimate the parameters of the model. And if you do so for the multinomial distribution, you're going to find that your best guess for the probability of any given outcome is the fraction of times that outcome was observed. For the Gaussian, you're going to find that your best guess for the mean of the Gaussian is just the average of your observations, and the best guess for the variance of the Gaussian is the average of the centered second moment of the observations. I mean, these formulae are familiar with you, to you, right? But where they come from is from the maximum likelihood principle, which in turn is based on the idea that whatever you're observing is extremely typical of the process that you're modeling. Questions? Anybody on Zoom? Is there anyone on Zoom? Mm-hmm. Okay. Cool. Okay, these are simple. Who's bronze woodpecker? Is there a bronze woodpecker? No. There's an indigo rabbit in class? No. Is there an indigo rabbit? No. Or an emerald eagle? The entire class is absent today. Coral hippo? Okay. There's an indigo shark. No? Okay. There's a blue hippo. I give up on you guys, right? Somebody want to answer the first question? True and true. Thank you. Okay. Whoever replied, thank you. Whoever didn't, shame on you. You should be in class. So maximum likelihood estimation is based on the theory that the world is a terribly boring place, right? So it estimates the values of the parameters of the distribution such that they maximize the probability of the training data. So far, so good. Nothing new. But then you have the situation. Sometimes the data that you're given might be incomplete. So they're missing something which makes it hard to estimate your distribution. And this can be for different reasons. It could be because maybe the data themselves are missing some components. Or maybe there's something about the structure of the model which makes you miss some information. So let's look at this first instance. Let's say I'm trying to estimate a Gaussian distribution from a collection of data. Except, so each column in this picture represents a vector. Except some components of each vector are missing. So this sort of thing happens, for example, if you are trying to compute the distribution of movie ratings for people. So everybody's seen a bunch of movies, they assign ratings, but not everybody has seen every movie, right? So the blacked out regions values would be the movies for which you did not provide any rating because you haven't observed them, you haven't seen the movies. So now you have partial data. Each person has given you a vector with some components missing. How do we compute the probability distribution of these data? How do you compute the Gaussian distribution given a collection of partial vectors? So what would be a good way of doing this? Here's the thing. Our Gaussian distribution is defined over the entire vector, right? So the Gaussian probability distribution is specified for a vector that includes all components, including the components that you did not see. On the other hand, some of these components are missing. And so if we look at the data that we have, these are the data we have. And these things are missing. So given this partial data with missing components, how do you go back and how do you go ahead and estimate the probability distribution or the parameters of the Gaussian? Now, here are the actual data we have. I can segregate it into two parts. The vectors of observed components, which are represented as O, and the vectors of missing components, which are represented as M. Now, any individual vector is a combination of both the observed components and the missing components. It's both O, a combination of both O and M. But the maximum likelihood principle says that you must maximize the likelihood of what it is you observed. And what have you observed? You only observed the O's, the green components. You've not observed the black components, which means that the maximum likelihood principle requires you to estimate the mean and the variance that maximizes this term to the left, the sum over all observations of the log probability of the components that you have actually observed. On the other hand, the Gaussian is defined over the entire vector, including the observed and missing components. So in order to compute this guy, obtain this guy, log of P of O, I should derive P of O from P of X, where X includes both observed and missing components. And the way you do it is to marginalize out the missing components by integration. And so when I plug this into my maximum likelihood estimation formula, the probability distribution for the observed data is going to be the sum over all vectors of the probability of the observed components of the vector, which is derived, or of the log probability of the observed components of the vector, where P of O is derived by integrating out M. So this results in a estimation problem of this kind, where I have to maximize a term which is a sum of logs, where within each log I have an integral. Now this is an ugly function. You can't just differentiate it and equate it to 0 and try to hope to find a maximum. It's not solvable by simple means. So does that make sense to all of you guys? So that was the first case where you had missing components in the data. But then you have the alternative where there's something about the structure of the model that makes data go away. So for example, let's say a Gaussian mixture. How many of you are familiar with Gaussian mixture distributions? Some of you, right? So consider some data for which the histogram looks like this blue curve. Now there's no nice closed form function, density function, which gives you this blue curve all by itself. The way we like to do it is to model it as a sum of several Gaussians, all scaled appropriately. So in this case, that histogram, that probability distribution might be modeled as the sum of the 4 Gaussians shown in the picture. And so the probability of any observation is going to be the weighted sum of the probabilities assigned by multiple Gaussians, which is shown by this formula here, which is P of O is the summation over all Gaussians of the probability, the weight of the Gaussian, P of K, times the probability assigned to the observation by the Gaussian. And now the standard problem has given a number of samples from this distribution. We want to estimate the parameters of all the Gaussians and their weights. Now, the Gaussian mixture model actually has an underlying generative story to it. What we are saying is that the data could have come from one of 4 Gaussians, depending on which mode the data lies in. And so the overall generative process is 2 steps. In the first step, we select a Gaussian according to the weight assigned to the Gaussian. In the second step, we draw an observation from that Gaussian. And so if you look over the entire set of draws, where different observations could have come from different Gaussians, the overall probability of any observation is, since any observation could have been generated by any other Gaussians, the overall probability is the sum over all Gaussians of the product of the a priori probability of the Gaussian and the probability assigned to the observation by the Gaussian itself. So this is PFO. This lecture would be easier if I had my microphone, right? And our objective is to learn the parameters of all of these Gaussians and the weights. Now, if I want to learn the model precisely, in the process of generating any given observation, there are two steps. In the first step, you select the Gaussian. In the second step, you draw an observation from the Gaussian. So I'm assigning colors to the Gaussian. If you want to learn all steps of the generating process, for each observation, you need to know which Gaussian was selected and what vector was drawn from it. So what you would really want to know is the color of the Gaussian and the vector. You would need this for every single observation. If you had this, then estimating the parameters of the model is easy. You can just separate out the observations, segregate them by the Gaussian identity. So you can separate out all the blue vectors, all the red vectors, all the green vectors, and then the mean and the variance of the blue vectors give you the mean and the variance of the blue Gaussian. The mean and the variance of the red vectors give you the mean and variance of the red Gaussian, and so on. Easy, right? But more realistically, you don't really know which Gaussian generated any given observation. So the identity of the Gaussian is missing, which means that you can't segregate the data and estimate the Gaussian parameters individually anymore. What we really want is a combination of the observation vector and the Gaussian k. What we are getting are just the observation vectors without the Gaussian identity. And once again, the maximum likelihood principle requires you to maximize the probability of what you have observed. That's all you really have, right? So this expects you to maximize the log summation over all observations of the log of P of O, except P of O itself is the sum over all Gaussians of the joint probability of the Gaussian and the observation, because in any given draw, you first draw the Gaussian and then draw the observation from the Gaussian. And so, which is, the sum over all k of P of k times the Gaussian. And so when we perform the maximum likelihood estimation, we find ourselves having to maximize this particular function, which is the sum over all observations of the log of the probability of the observation, which in turn here gives you a sum over all Gaussians of the product of the probability of selecting the Gaussian and drawing the observation from the Gaussian. So because we don't know which Gaussian any given vector came from, we are going to have to marginalize over all the Gaussians, which means you're summing out the Gaussian. And so as a result, you end up with a sum inside the log, and once again you end up with a situation where you have to maximize a function which is the log of a sum, which is a very ugly function, and it's hard to maximize. Yes, Karthik?
This ignores the possibility that an observation vector could influence two Gaussians.
No, this is the generative process. Okay. You're saying that when you see the observation, you have no idea which Gaussian it came from. So this is literally saying that this is the probability that you chose the first Gaussian and the observation was drawn from it, plus the probability of having chosen the second Gaussian and having obtained the Gaussian from it, and so on. So you're considering every possibility for which Gaussian the observation vector must have come from, right? And because you're summing out all of the Gaussians, you end up with a summation inside the log. Now this is all fairly straightforward. The key point here is that there's missing information. When I was trying to estimate the Gaussian distribution from incomplete vectors, there were components of the data that were missing. I had to integrate them out. when I was trying to estimate the parameters of the Gaussian mixture, I didn't know which Gaussian each observation vector came from. And so I had to marginalize out the identity of the Gaussian. And thus, in each case, when I maximize the log likelihood of the observed data, I have to integrate out whatever it is I have not observed. And I'm representing things that I have not observed by the symbol H, which is to say it's hidden. You're not able to see it. In the case of the Gaussian data, you're not able to see the missing components. In the case of the Gaussian mixture, you're not able to see the identity of the Gaussian. And so we end up with a situation where we have to maximize, with respect to theta, the log of the integral of, or the marginal probability of P of O, which is the integral or the sum over the hidden parameters, hidden terms, of the joint probability of H and O, as we have in the formula. So in the Gaussian data case, H was the components that were not observed. In the Gaussian mixture case, H would be the identity of the Gaussian. Regardless, the issue is that in all cases, there is a summation or an integral within the log, and this makes direct optimization of this log likelihood very hard. And so we need some tricks. Now, this is the general form of the problem, and the real issue happens because you have a summation inside the log, or an integral inside the log. So can we do something, perform some mathematical trick such that this thing can be made more tractable? So the log of a sum is hard to optimize. Can we do something about it? Can we come up with an approximation that removes the sum from inside the log? So this is the method of variations. And for this, we introduce the notion of a variational lower bound, which is based on this very simple principle. The log of P of O is simply the sum log of the sum over all the missing terms, H, of the joint probability of log of the joint probability, no. The log of P of O is the log of the sum over all missing terms of the joint probability of the missing term H and the observed data O. And I can multiply and divide P of H comma O by some function Q of H. And Q of H has this characteristic that it's non-negative, it's always 0 or greater. In fact, we can assume that it's never 0. And it's never 0 when P of H comma O itself is not 0. And it sums to 1. So in other words, Q of H is also a probability distribution over H. Now, when I write it like this, then what we have inside the log is the sum over H of Q of H times P over Q, right? Now, we invoke a property of the log function. The log function is concave. What I mean by a concave function is that it curves downwards. So in other words, if I have two values x1 and x2, then if I compute log of x1, that's this value here. If I compute log of x2, that's this value over here. So any convex combination of log of x1 and x2 is going to rely on the red line that connects those 2 points, right? It's going to be some a times log of x1 plus 1 minus a times log of x2. On the other hand, the log of the convex combinations of H, log of a times x1 plus 1 minus a times x2, is going to lie on the blue curve itself. So this guy here is the red curve represents some q times log x1 plus 1 minus q times log x2. The blue curve represents log of q times x1 plus 1 minus q times x2. So this blue curve represents the log function computed on this x. The red line represents some interpolation between the logs at the boundaries. And what we observe is that the red line is always below the blue curve, right? So in other words, the red line is a lower bound on the blue curve, regardless of what x1 and x2 might be. So we can generally say that the convex combination of the log of the x's is going to be lower than the log of the convex combination of x's, because the log function is concave. And using that property now, I can say the log of q of h times p over q. If I think of p over q as my x's, the q's represent a set of non-negative values that sum to 1. So this term over here is the log of the convex combination of p over q, which represents the blue curve. This term over here represents the convex combination of the log of p over q, which represents the red line. And so the term to the left is always going to be greater than the term to the right. So the term to the right is a lower bound on the term to the left. And so by the concavity of the log function, we can say that the term to the left, of course, is the log of p of h comma o, right? So we can say that the log of, the term to the left is log of p of o, because it's summing over h. So we can say that log of p of o is always going to be greater than or equal to the convex combination, any convex combination of log of p over q. So this is just some math which gives us a lower bound on the log probability of the data. Again, guys, I apologize for being rooted over here. It makes this much harder to explain, but I don't have my mic. So this term to the right, which is a convex combination of p of o comma h comma o over q of h, right? This term is a lower bound on the actual log probability of the data. It's what is called a variational lower bound. And when we actually begin sticking data in, it's the empirical lower bound. So how does this help us? Here's how it helps us. The term to the left is the log probability of the observation that you want to maximize, right? The term to the right is the convex. You over there at the back, are you taking notes? No, the one in front of you. Can you tap them? Are you taking notes? Yeah. Okay. Right. So anyways, so the term to the right is the lower bound, right? And it's meaning it's guaranteed to be no greater than the log probability of the observation itself. And so here's what you've got. The red curve might be the actual log probability of the data as a function of theta. The blue curve is the lower bound. And so the lower bound always lies below or at the red curve. A tight lower bound is a choice of Q that makes this lower bound curve as close as possible to the red curve itself. And once we can come up with a lower bound of this kind, if the lower bound is tight, instead of maximizing the red curve, we can maximize the green curve. And we can say, okay, if I maximize the green curve, maybe the red curve is also maximized. And that's the property that we will actually use. Because we found that it's impossible to maximize log of p of o, because log of p of o is actually log of p of summation over h, p of h comma o, and h is not seen. So instead, we are going to maximize the lower bound, which is summation over h q of h log of p of h comma o over p of o. And what happens in the term to the right is that the summation inside the log goes away. So now we can replace this problem with a two-step function, a two-step solution, where we say we first find a q of h such that this lower bound is as tight as possible. And then once we find that q of h, we can fix that Q of H and find the theta that maximizes the lower bound. But then once you find the theta that maximizes the lower bound, you can go back and repeat the process and find a new Q of H, which makes it an even tighter lower bound, and repeat the process. So the first step would be this, which is where you want to find a Q of H that such that the lower bound is as tight as possible. So you're maximizing what is called the variational lower bound. And the second step is, given the lower bound, you are trying to find the parameters that theta that maximize the lower bound. And a special case of this is the expectation maximization algorithm, when Q of H is the conditional probability of the missing components H given the observations and the previous estimate of the model parameters. So we have a poll, but then we'll try to see what all of this crazy math really means, because there's no point in, math is all fine. And I'm pretty sure none of you really got what I said, because it's impossible to understand math from slides, in my experience. I must present it because it's required. Okay. Does anybody want to answer the first question? Is the first statement true or false? Second one? And third? It's not providing you any kind of closed form formula, right? It's an iterative process. If it's iterative, that means there's no closed form. You're estimating a Q of H, then you're estimating the model parameters. What about the second one? Second statement. The second question, is the first statement true or false? True. Second? True. It's going to, the way we do it is the function of the model parameters. And what about the third? False. It's a lower bound. It cannot be greater than the function itself, right? So all very good. That's so much math. But what are we really doing? In my experience, nobody understands math, right? But everybody gets pictures. So I hope the guys on Zoom can hear me. But suppose I give you a collection of vectors of this kind, where these components are missing, and from this I must estimate a Gaussian distribution. Yeah. So what is the best thing you can do? I've given you a bunch of movie ratings, except I didn't give you the rating for some movie, right? So these are incomplete vectors. How can you, we know that Gaussians are defined over complete data, right? So what can you do with these vectors to make them amenable to estimating Gaussian parameters? What would you do if you were given this data as an engineer or as a data scientist? What would you do? Anybody?
You could fill it within data.
So you can fill up this data, right? Just guess this value. And if I guess this value, then I have complete vectors. The problem is easy, right? But what are you going to guess this value to be? What must this value be? How do you guess it?
I would try to sample it from the distribution. So using what that could.
So what you can do is, Josh says that I can look at this data and maybe fill up the mean. Would that be sufficient? How else would you fill it? Anyone?
Maybe I would use the mean of the value of the previous value and later the following that value.
Interpolate.
Yes.
But then you're assuming that they're all continuous and smooth, right? Statistically, what would you do?
Or maybe draw from another distribution.
Which distribution?
The one that we observe,
The one, but
the observed distribution.
then that's, let's say this is, let's say these are all war movies, and this is a movie on, one of those romantic movies. Will the mean of all the war movies give you a rating for the romantic movies?
Based on the distribution of that data and based on all of the observations.
Okay. So here's what, I'm going to try to speak loudly. Here's what I can do, right? Think of a simple two-dimensional example instead of many dimensions. This is going to be, the Gaussian is going to be some kind of a bell shape. That's the distribution, correct? So if I've got a two-dimensional example, a data instance where I have not given you one component, then what am I really doing? So this is my component x1, this is my component x2. I have not given you x1, I've given you x2. So I know the value of x2 at this point, correct? I can slice the Gaussian at that x2. Now this is a two-dimensional bell. If I slice the Gaussian at that x2, what will the slice look like? Anybody?
Gaussian?
It's going to be a Gaussian too, right? If I take any two-dimensional Gaussian and slice it, that slice itself is going to have a Gaussian face, correct? And then, what is this Gaussian face telling me? What is that Gaussian face? That is the probability distribution of P of x1 given x2, right? I fixed the x2, I've sliced the joint distribution of x1 and x2, and it's giving me the conditional distribution of x1 given x2. I've given you the hint. Once I have that, what am I going to be filling this value with? Would I be doing random interpolations, or what would I do? Anyone?
Maximum probability.
So, here's the thing. You told me earlier that if I have the Gaussian distribution, I just pick up the mean, right? But if I pick up the mean value for x1, I'm ignoring x2, which I have observed, right? Instead, I can say what is the distribution of x1s at this value of x2? Which of the two is going to be the better one to get my data instant, my missing value from? The second one, right? That makes sense to everybody? And so that is basically what we are going to do. So we have some missing components and we have some observed data O, right? And so consider a single vector of this kind. It's got some missing components shown by the black value. The green data are shown. And we're going to try to fill this missing data into the value somehow. And the way we will fill it is I can actually pick one value, right? But then is it all, let's say I'm looking at the joint distribution of say heights and weights, right? Heights are correlated with weights. So if I told you that the person was 175 centimeters tall, then in this missing component where the weight is missing, what is the weight you would fill in? You're going to fill in the average weight of all people who are 175 centimeters tall, correct? You're not going to pick up just the average weight of all human beings because that's going to include short and tall people, right? You're going to pick the specific set of people who are 175 centimeters tall. And so that's what you're going to fill over there. But then if you do that, you're just picking one value, right? Instead, you can consider the entire distribution. So you can think of it as saying, I'm making many copies of the vector, and I'm going to fill in the missing value with every possible value of height. So I'm going to of the missing components. So in this example, I can say I'm making many copies of the vector, and I'm going to fill every possible value for the weight, except that the weights that are more probable for people who are 175 centimeters tall are going to be more frequently filled in, and the less probable ones are going to be less frequently filled in. So instead of picking just one, you're representing the entire distribution. That makes sense? Right? So, and now, so in other words, I'm going to be filling in the missing components, making many copies and filling in the missing value by drawing from the distribution of this missing value given the observed value. So in this example, I'm going to be just filling in the weight by drawing from the distribution of weights for all people who are 175 centimeters tall. That makes sense? Right? And so once I do that, what happens? My data are complete. All the missing components have now been filled in through a guess, right? And then I can use my completed data to, so where in each instance, the missing components have been drawn from the conditional distribution of the missing components given the observed components. And now I have complete data, I can go back and estimate my Gaussian parameters, right? So this was where I was trying to estimate the Gaussian parameters. The same thing with Gaussian mixture distributions. For each vector, I do not know the identity of the Gaussian. Can the Gaussian folks in Zoom hear me? No. Not really? That's too bad, okay. So over here, for every vector, I'm trying to estimate I do not know the identity of the Gaussian. So what can I do? If I look at the Gaussian mixture distribution, let's say I have some value x over here. From the Gaussian mixture distribution, I see that the green Gaussian is more likely to have generated the vector than the red Gaussian, right? So the red Gaussian in turn is more likely to have generated that vector than the blue Gaussian. And so I have a conditional probability distribution for the Gaussian identities given the data instance. And so we know that every Gaussian is capable of generating this vector. What I will do is make many virtual copies of my vector, or I could, and I'm going to fill in the color using every possible value for the Gaussian itself, where the number of times I'm going to fill in blue is going to be proportional to P of blue given vector. The number of times I fill in red is going to be proportional to P of red given the vector, and so on. And once I do that, and once I do that, my data are complete, and I can segregate the red, blue, and green vectors out and re-estimate my model parameters. So the question now here becomes this. I'm assuming that when I'm filling in the data, so I won't get too deeply into the math, but the whole point is this. We are filling in this missing component by drawing from the conditional probability distribution of the missing components given the observed data. That makes sense to everybody? As a high-level concept, that's the key piece. The rest of the math is quite irrelevant as far as we are concerned. So where does the conditional distribution of the missing components come from? Now, to compute the conditional distribution of the missing components, you need the overall probability distribution itself. We don't have that, right? If we had that, we wouldn't be going through this business of estimation. So we are already trying to estimate something, and yet we need the conditional probability distribution of the missing components given the observed components. So the way we do it is in the iterative process. At each step of the estimation, you have a current estimate for the overall probability distribution. So from the current estimate, you can compute the conditional probability of the missing components given the observed components for any data instance, right? And then you can use that, you can sample from that to fill in the missing components. Now we have complete data. Using the complete data, you can go back and re-estimate your complete distribution. And now that you have the completed distribution re-estimated, you can use that once again to go back and and determine the conditional distribution of the missing components given the observed data, and and use the updated distribution to go back and fill in the missing values, and repeat this process. So to go back to our height weight example, let's say I have a collection of data for where for some people I know the height, for others I know the weight, and maybe for some I know both, right? So I would start off by coming up with an initial estimate for the joint distribution of heights and weights. Then for each vector where I know the height but not the weight, from the current estimate of the joint distribution, I can compute the conditional distribution of weights given heights. And from that, I can sample the weight and fill in the missing weight. So now I have complete data. Now using this complete data, I can go back and re-estimate my distribution. Now from the re-estimated distribution, once again, I can come back, I can compute the conditional distribution of heights given weights and weights given heights, right? And from these updated conditional distributions, I can go back and refill the missing values and repeat the whole process. That make sense? Right. So this is the overall process of estimation when we have missing data. There's a lot of math behind it. There's a lot of mathematical proof, but the concept is very simple and very easy to absorb. And the concept here is that when you have some missing data or missing components, you want to fill in the missing components. And the way you fill in the missing components is by drawing from the conditional distribution of the missing components given the observed components. So once you fill them in, you have the complete data. Once you have complete data, it's easy for you to estimate the model parameters. And once you've estimated them, but then because this is an iterative process, we're sort of iterating. We start off with an initial guess for the overall data probability distribution, from which for each incomplete data instance, we derive the conditional distribution of the missing components given the observed components and sample from it to fill in the missing components. Once you've completed the data, you can go back and re-estimate the model parameters, and you repeat this. Questions? That makes sense even. Questions on Zoom? Okay. So I have a whole lot of slides explaining all of that, but maybe this poll captures it. Pardon me? Okay, guys. Somebody want to tell me someone on Zoom, is that first statement true or false?
True.
True, right? In each iteration, we complete the data by filling in the missing components and estimate parameters from the entire completed data. What about the second one?
True.
Also true. The third one?
True.
And the fourth? False, right? Because it's an iterative process. What we are really doing is, the point is this, we are completing the data. And we're completing the data by using the conditional probability of the missing components given the observed components. And we are re-estimating model parameters using the complete data. But then once you re-estimate the model, you're going to use this once again to go back and derive an updated distribution for conditional distribution for the missing components, fill in a second time, and then keep repeating this process. Yeah.
Third sentence. Okay.
There are two different ways of doing it, right? I can think of this as saying that when I have any given vector, I can I can do one of two things. I can fill in the missing component in every possible way, except I make multiple copies. And the number of times any possible value is filled in is proportional to P of m given out. Or I can do it just once by simply sampling once from P of m given out.
Okay.
Right? That's it. Yeah.
When does this process, like when do we stop, or is it like a arbitrary that we can stop it?
So because this is a maximum likelihood estimation model, you would stop when the likelihood of the observed data converges, which you can always compute, right? So, all right, I'm going to switch gears for a bit. How many of you are familiar with principal component analysis? Most of you must be, right? What is PCA? You're given a set of centered data, centered meaning the mean is 0, and we want to find the principal subspace such that when all the data are projected onto the subspace, then the total squared error from the projection over the entire training data is minimized, right? You never thought of this as a statistical estimation problem, but this is actually a generative model. How so? Here's what PCA really does, right? You want to find the principal subspace such that when all vectors are approximated on that subspace, the approximation error is minimal. So basically, we are sort of searching through all possible subspaces until we find the one subspace where the total error from projecting every data instance onto that subspace is minimized. Now it just so happens that when you perform standard PCA, this business of projecting the data onto a subspace is very easily computed. It's just an inner product between the data vector and the principal vectors of the subspace itself. And so every data vector x is going to be can be projected onto the subspace where the length of the projection, shown by the curly brace over here, is simply the inner product between the data vector x and the normal to the subspace. And so once you write it that way, you can actually compute the error between the data vector and its projection on the subspace. So you can compute the squared error. This is just the standard Pythagoras theorem. Norm x squared is the length of the vector. Norm x transpose w squared is the length of the squared length of the projection. The difference between the two is the squared length of the error, right? And this I can write a formula out for. I can sum this over all of my training data. I can minimize it, and you get your standard formula for principal component analysis. The optimization tells you that you have to compute the correlation, the covariance matrix of your data, and the eigenvectors of the covariance matrix are going to give you the directions for the principal subspace. All very nice. This is easy. The math is easy, right? So whenever we thought of principal component analysis, there was always a closed form solution. And the closed form solution required us to compute the covariance matrix and compute the eigenvectors of the covariance matrix. But there's an iterative solution too. How many of you have heard of the iterative solution for principal component analysis? Nobody? Okay. Again, our objective is to find, if I'm looking just for a single principal subspace, a single principal component, you can generalize this, is to find this vector W such that when every data instance is projected onto the subspace defined by W, the squared error is minimized, right? So here's how I can do it. I can take an initial guess for W, and then I can project the data vectors onto W. And then from the projections, I can go back and re-estimate W. and keep repeating this process. So how would this work? It's going to look something like this. So I try to do this with a, this is horrible, but MATLAB did something really bad. So here's how it would work. I'm not sure I can actually disconnect this gooseneck from here. If I could, all right. So here's how it will work. We are given a bunch of data instances, right? We are trying to find a vector W such that the sum of these squared lengths is minimized. So you can think of it this way. For each of these data vectors, I'm attaching a ball on this. I think of the line as maybe a very thin rod on which I can put in beads. Okay? And so corresponding to every one of these data vectors, I put in a bead on the rod. And I attach the data vector to the bead. Now the tension in the rod, in this attachment, in the string, is proportional to the square of the length. Okay. So then what are we really doing? What we are doing is this. We are finding this vector such that the total tension in all of the strings is minimized. Make sense? Right. So what would happen? I can, if I just attach this rod over here and let it be, then if I put a whole bunch of beads on this rod and attach each bead to a data vector, then the rod is going to rotate until the total tension in the strings is minimized, right? But furthermore, two things are happening. One is for the individual string to have the lowest possible tension, the bead must be directly below the data instance, right? And the rotation of the, so if I fix, we have the eraser here. Yeah. So did this analogy make sense to you guys, right? So if it does, here's what I can do. If I got all of my data instances, and I have my rod, and I attach each data instance to a bead, and the bead is allowed to slide along the rod, what would happen to each bead? What would happen to each bead if you're trying to minimize the tension? Anyone? For any given, when is the tension in the string minimized? When it's perpendicular, so the bead is going to slide, go down here, right? So every single bead is going to come perpendicularly under the data instance. So if I fix the rod, every bead is going to come directly under the data instance, right? This is good. Now suppose I did something else. For each vector, I actually ensured that I put the bead directly under the rod, right? But I only allowed the rod to rotate. So I fix the beads. Okay, I start off like so. So in the first case, we agreed that for any data instance, if I attach it to a bead of this kind, the bead is going to move over and go directly below the data instance. This we agreed, right? Here's the second thing I will do. I have my data instances, I have my rod, And for every data instance, I start off by placing the bead directly beneath the data instance. So locally, every single string has minimum tension, but then I let the rod rotate. What would happen? The rod is going to rotate so that the total tension in all the strings is minimized. Correct? That makes sense? Because you're still trying to minimize the total tension. So there's this trade-off between what happens to the individual data instances. For each of the individual data instances, it wants the bead to be directly underneath it. But the rod by itself wants the total tension in all of the data instances to be, all of the strings to be minimized. So that gives me this two-step process. In the first step, I can start off by just initializing this rod, which is my principal subspace. Okay, and I can just attach the data the beads just below the rod and let the rod rotate. And the rod is going to rotate to a new point where the total tension in all of the vectors is minimized. Then once it has done so, this will rotate to something like this. Maybe I'll have to see if I have the. I'm not sure why I don't have the pictures. So you can see what happens, right? This is the iterative process. I can start off by initializing my W and projecting all the data vectors onto this W. Then I can just let only the rod rotate, and it's going to rotate until this analogy is failing badly without my pictures and my ability to go away from the mic, but let me try this anyways. Let me do this with only two data instances. So let me say I have these two guys, and my initial vector is like so. So initially I'm going to stick my two vectors over there and attach my data instances to the beads. Now this tension is quite high because this guy is long, right? So what would happen is this is going to rotate, and it's going to become something like this because this will minimize the overall tension, because the tension in the strings is proportional to the square of the lengths, right? But if it does so, in the process of rotating this way, this string is no longer going to be, these strings are no longer going to be perpendicular. Although the total tension in the rod in the strings is minimized, the individual strings are no longer going to be perpendicular to the rod. Now I release the beads. If I release the beads, what happens? Each bead is individually going to become perpendicular again, right? And so now individually, now this guy is going to become here, and so this goes here, and this goes here. So, but then now I attach the strings. When I attach the beads, then it's going to try to minimize the total tension in all the strings. And so then once again the rod will rotate. And so here's the two-step process. In the first step process, I'm going to try to optimize the projections given the basis. Then second, given the projections, I'm going to try to optimize the basis. And this is an iterative process, going forward and backward until I find the optimal subspace. Okay? So basically, this is an iterative process where given x, what we are really doing is this. You have my data x. You're trying to find the principal subspace W and the projection Z such that the error between x and WZ is minimized. And we will do this in a two-step process. First, we fix the W and estimate the Z. Then we fix the Z and estimate the W. And we're going to keep going forward and backward. So the math is going to be that Z equals 0 and W times equals x times total inverse. So if I just keep iterating this, you're guaranteed eventually to find the same optimum as you did if you simply solve your eigenvalue equation, right? So here's what we're doing. You start off by initializing the W, and from the W, you're estimating the Z. Then you fix the Z, and then you estimate the W. Then you fix the W and estimate the Z. And if you go through this iterative process, that too is going to give you your principal components, PCA, right? So here is the overall process. From X, we are estimating Z, and then given Z, we are estimating W. Basically, we're reconstructing X, right? If you draw it this way, it looks like an autoencoder, which is why in the last class, we said a linear autoencoder is actually performing principal component analysis, right? And you can use back propagation rather than the closed form formula. Now, there's one little issue over here in that when I write it this way, I can if I say X equals WZ, there are many different solutions which will give me the same approximation error. So for example, I can say X equals W times U and Z equals U inverse times Z, right? So this is also going to be give me the same solution. So there's a non-standardness in that there are many different solutions which all give me the same approximation error. So I can impose an additional constraint on Z. So there's a scaling variant, it's scaling invariant. I can increase the length of W and decrease Z. Or I can increase Z and decrease W. The solution is not unique. And to bypass it, we can impose some constraints. You can say that the length of the vectors in W is always 1. That's your standard principal component analysis. But then there's something else we can do. We can say that the Z values must have a standard Gaussian distribution over your training data. And both of them are essentially going to give you the same principal subspace. They're just going to give you different bases, right? Both will perform principal component analysis. So the linear autoencoder that we saw in the last class is actually performing principal component analysis. And if you want to get a unique solution instead of one of many solutions, then you can impose an additional constraint that the hidden value Z must have a standard Gaussian distribution. So far so good, right? So what exactly is the iterative solution doing? I mean, math is all very funny, fine, but it's better to do this with pictures. I'm given a collection of vectors. I want to find the principal subspace. So in the principal subspace, the first thing I'm doing is I'm initializing my principal subspace, right? And then from the principal subspace, I'm finding the projection Z or the coordinate Z on this principal subspace such that the projection error for the individual data instances is minimized, right? But then subsequently, given the coordinates, I'm going back and re-estimating my principal subspace using these coordinates. And that's going to give me a new principal subspace. Then on this new principal subspace, I'm going to go back and re-estimate my coordinates. So the colored boxes on the bottom, they are the coordinates of the points on the principal subspace. And when you're typically given the data, you're given neither the principal subspace nor the coordinates. So the iterative process is initializing the principal subspace and finding the coordinates. Then given the coordinates, it's going back and finding the principal subspace and repeating this step back and forth. So what does this look like? This is just the same as the EM approximation, EM method that we saw earlier, right? This is EM. So it turns out that the principal component analysis is actually a maximum likelihood estimator, where you do get a closed form solution, but you can even have an EM solution where you're doing a two-step process, where for each data instance, you're first finding the coordinates of the data instance on the principal subspace, and then given the coordinates, you're re-estimating the principal subspace, and repeating this process back and forth. So here's what PCA looks like. If I assume, just to enforce uniqueness on the solution, that Z must have a unit variance, it must come from a standard Gaussian, then the decoder of the principal of this linear autoencoder is in fact a generative model. What we are doing is drawing a sample Z from a standard Gaussian and then passing it through this decoder to generate new samples. So PCA actually has a generative story. The generative story in principal component analysis is that in order to generate any data instance, you're first drawing a sample from a standard Gaussian. Then this standard Gaussian data is being transformed through some linear transform, which is placing you on some location in the principal subspace. So basically you're taking a Gaussian step on the principal subspace. And then having taken a Gaussian step on the principal subspace, in the second step, you're taking a Gaussian step orthogonal to the principal subspace. And that's eventually giving you your data vector. So once again, the point is PCA is actually a generative model, ignoring all of the math that we've done so far. The underlying story between PCA is this, that anytime you generate a data, you're going through a two-step process. You're drawing a sample from a standard Gaussian, and you're transforming it through a linear transform, and then you're adding some noise to it. But literally what you're doing is you have some principal subspace, you are taking a Gaussian step on the principal subspace, and then you're taking a step orthogonal to the principal subspace where the length of the step is also distributed according to a Gaussian. And that eventually gives you your final data vector. I know this is all very confusing because I've done a horrible job of explaining this today, but I should not forget my mic in future. But the point is, the key take-home lesson is that we have already dealt with a generative model for generating Gaussian data in our lives if we have ever dealt with PCA. We are assuming that the data has a Gaussian distribution. And PCA itself is a maximum likelihood estimate of the parameters of this distribution, except the data distribution is decomposed into the step of sum of two Gaussians. One is a Gaussian distribution on the principal subspace, and the second is a Gaussian distribution orthogonal to the subspace. And the sum is still going to be Gaussian, right? So the PCA, if I were to draw a neural network variant of the PCA, this is what it's going to look like. You have a Gaussian random variable Z going into a linear layer, as shown by the picture. And the output of the linear layer, to the output of the linear layer, you're adding a second Gaussian random variable E, where E has this characteristic that it represents noise that's exactly orthogonal to the subspace and nothing else. And so the overall distribution, so if you want to estimate estimate the PCA model, the encoder is computing Z from the data, the decoder is reconstructing the data from Z. Right? And the overall distribution that PCA models as a Gaussian, that the data itself has a Gaussian distribution. Now what has this got to do with variational autoencoders? We'll get to this in the next class. Okay. Anybody want to tell me which of these statements are right? 1, 2, 1, 5. Thank you. So I'll stop here, and we're going to be talking on Wednesday's class. We're going to be talking about actual business of learning variational autoencoders, where we will combine two concepts: the concept of filling in missing data that we just saw, and the concept of a generative model of this kind, where data drawn from a distribution is actually transformed to give you a principal subspace. And we'll see how that happens in next. Thank you. Questions? There's no class on Monday, I said, right?
So, is there a Wednesday class?
There is a Wednesday class. Thank you, everybody.